we'll see first the acids and bases. So this will be part of our uh, reaction reagents, right? So in order to understand reagents, the first thing which we are going to see is this, that is acids and bases. So the definitions of acids and bases are many, and so that's why we begin our study of these reactions and mechanisms by examining some of the basic principles of acid-base chemistry. So some basic principles is what we are going to see here. Many of the reactions which occur in organic chemistry are either acid-base reactions themselves or they involve an acid-base reaction at some stage. So either they'll be a completely acid-base reaction or they'll involve acids and base reaction or as one of their steps. Okay, and acid-base reactions are simple fundamental reactions which will enable us to see how, I mean, we used how these curved arrow notations are used to represent mechanism of reactions. So in the reactions, you must have seen many places there is arrows like this or arrows like this. So these things we will try to understand, and this the basic of all these notations are actually understood by these acid-bases reaction mechanism, and it is also you can say that it depicts the process of bond breaking and bond making that occurs as molecule react. Okay, so the first definition of acid and base is given on the basis of Bronsted-Lowry acids and bases. So that is Bronsted. So these are the name of two scientists, Bronsted and Lowry, acids and base. Okay, so it was the first definition. Two classes of acid-base reactions are there, that is Bronsted-Lowry acid-base and Lewis acid-base reactions. And this is our first, and one more is there, which is Arrhenius. So that we'll leave for the timing, and we'll see when it comes in physical chemistry. So what is Bronsted? According to Bronsted and Lowry, uh, the reactions involve transfer of proton. And how do we show a proton? Proton is actually H plus. So in hydrogen, there is one proton and one electron. So from that hydrogen, if one electron leaves, that means there is only one proton left, and that's why this H plus is represented, or proton is represented by H plus. So a reagent, when this reaction occurs, a reagent or a substance will be donating or losing a proton, and another will be accepting that. So the proton donor, the one which donates, the proton donor is called acid. And it is very easy to remember. Suppose, for example, HCl is acid. Why? Because when it breaks, it will give H plus plus Cl negative, right? Or you can say that it is giving both H plus and Cl. So now see this, for example, NaOH plus HCl. What happens now? This gives out H plus and this gives out OH negative. So the compound which is formed is NaCl plus H2O. So H plus was given by HCl. So that's why this HCl is actually a Bronsted-Lowry acid, and this has actually accepted the H plus, right? Actually NaOH had OH. This OH accepted H plus and became H2O. So this is Bronsted-Lowry base. So this is the basic definition of acid and base according to Bronsted and Lowry's concept. So these are This is, in fact, the first definition of acid and bases which you must have studied when you were in junior classes. Okay, now what is, or based on this, we have several others, several other compounds which are divided or which are categorized in acids or bases. Now, what happens here is when we classify the reactions as either an acid or base, reactants as, I mean, either as an acid or a base, we also classify the product in a specific way. The molecule or ion that forms when an acid loses its proton is called conjugate base of that acid, right? So, for example, suppose we have the same example. Suppose we take H2O plus HCl, right? So this is called aqueous solution of HCl. And in that HCl, what will HCl do? It will lose proton. So that is also one of the definition that a compound which loses proton in its aqueous solution is called an acid. So what happens now? See, we'll see the bond structures. So we have this H, we have O here, suppose another H is here, and this O has two lone pairs, this plus HCl. Now, when we see HCl, it will be like this, correct? This bond means the bonds are there, two electrons from each of the atoms are being shared, and there will be this three lone pairs, that is total six electrons, which are not forming any bond. Now, what happens here? When it combines or when this aqueous solution is formed, this H, which is here, tries to break from here. It takes one electron from this. I mean, it gives its electron to this chlorine. Now, why will it give it, why H2 will give its electron to Cl? Because this is more electronegative. So because chlorine is more electronegative, the electron which is shared is actually pulled towards this. And when it is pulled towards it, H loses an electron. And what we will have after that, this H, which is actually H plus, that comes here. So remember now, H has no electron and this O has a pair of electron. So that H plus has vacancy or for two electrons, and this is the electron which is available here. So now what will happen due to this? We have something like this, okay? And this O will have only one lone pair. Now O had actually two lone pair. It has actually given its one of the lone pairs in, or it has contributed that or donated its lone pair for the cause of making this bond with or new bond with H. So that's why there will be a positive charge on O, right? And what will happen because H has left Cl, so this Cl will have these lone pairs, right? And it will have this extra lone pair from H. So that will also be there. Now chlorine's actual capacity is only 7, but it has one extra electron. So that means what? It has a negative charge on this. Is it clear? So now water in this case has accepted proton. So this will be a proton acceptor. So this will be called base. And because this HCl has donated H plus, so this is acid. And now the important part, when they reacted, then here in the final stage, what we see here is HO, H3O is formed. That is formed from water, and water was base. So now this will be called conjugate acid. A conjugate acid is formed from base, right? So this is conjugate acid of H2O. And same way, this is conjugate base of HCl. A conjugate base is formed from an acid, and a conjugate acid is formed from a base, right? So this chloride ion is a conjugate base, and this uh, H3O, which is actually called hydronium ion. So the name for this is called hydronium ion. And H plus or proton is actually present in this form. That is, mostly it will be written like this, H3O plus. So this is nothing but this. And this is called hydronium ion. And as you can see here, this is the conjugate acid of the base, which in this reaction is water. Clear? So the molecule or ion that forms when an acid loses its proton is called the conjugate base of that acid, and the vice versa is called, or the reverse of that, or the opposite of that is called conjugate acid. So hydronium ion is a conjugate acid. And see, it was base here. It accepted an electron, it accepted a proton and became something. Now, what is this capable of? This is capable of donating a proton. So that's why this is actually called an acid. So you can understand in that way as well. So that is Bronsted-Lowry acid and bases. And there are multiple examples for this. All those acids which contain hydrogen can be or will be examples of this. That is Hi plus H2O. This is hydrogen iodide plus H2O. So what will it give? It all will have same reaction, that is H3O plus plus I negative. Same way HBr, right? Now suppose we have H2SO4, that is sulfuric acid. So this sulfuric acid plus H2O, what will happen now? This sulfuric acid will give you again same thing, H3O plus, and in H2SO4 there will be only one left, right? And that is HSO4 negative. So we can say what is our base, and so wherever you are seeing this plus sign, right, that is actually our conjugate acid. So this is conjugate acid, this is conjugate acid, and the one which is left, that is actually its base. Even this, and if you see this H2SO4, now even this HSO4 negative, even this donates one more H in its aqueous solution to give again one H3O plus plus SO4, and now see what will happen. SO4, it is already a -1, so when it loses one more proton, it will be SO4 minus 2 or 2 minus. Now the extent to which an acid transfers proton to a base, for example water, is the measure of its strength or an acid. Acid strength is therefore a measure of the percentage of ionization, right? So in this case, if I say what is acid strength, or on what factor it will be depend. So it will depend on the percentage of ionization, percentage of, not the concentration, right? So that is Arrhenius, so that is Bronsted uh, acid and bases. And in this, you can see that Some of them are donating more proton per molecule, and some of them are donating less. So for example, this hydrogen iodide is is able to donate only one H plus here and make this. So this is doing only once. But if you see this here, it is actually donating two, or is able to create two hydronium ions. So such acids are called diprotic acid, right? So such acids are called diprotic acid. Protic means proton, di means two. So they are actually donating two protons. So that's why they are called diprotic acids. Okay, the transfer of the first proton occurs completely while the second is transferred only to the extent about 10%. So obviously the first transfer is easy. So that happens more, and the second one is little bit less. Okay, so hydronium ion is the strongest acid that can exist in water to any significant extent. Okay, and hydroxide ion is the strongest base that can exist in water to any significant extent. Now, when an ionic compound dissolves in water, the ions are solvated. For example, sodium hydroxide, if we take, right, the positive sodium ion are stabilized by interaction with unshared electron pair of water molecules. What does that mean? So you have a sodium ion, for example, if we talk about um, sodium hydroxide, right? So this sodium hydroxide has a sodium ion and OH negative ion. So even this OH is actually like this. There is an O and H, and here on oxygen, when this breaks, it will have an extra lone pair, so that's why there will be a negative charge. And Na has lost its electron, so it has a positive charge. Now there are lots of water molecules. It is actually an aqueous solution. So in its aqueous solution, that means there is a lot of H2O molecules. So what happens to those H2O molecules? H2O molecules can be written like this as well, an oxygen with two lone pairs. So there is a lone pair here. That means there is a, you can say, concentration of negative charge there. So these OH2, they are attracted towards this Na plus, right? So OH2, there is an electron cloud here that will be attracted towards this. OH2, again this will be attracted towards this. Why? Because there is a electron, lone pair of electrons there. And this O is having this negative charge. So what happens in case of, how water is solvated here? So there will be hydrogen, oxygen, hydrogen like this. This hydrogen will be attracted towards this. And these are not bonds. They are just being attracted towards oxygen. Hydrogen is attracted towards oxygen, that is in water, and O, that is oxygen, is attracted towards sodium. So now here again, this will be H, O, H, something like this. So this is our solvated sodium ion, and this is solvated hydroxide ion. So when an aqueous solution of sodium hydroxide is mixed with an aqueous solution of, say, some other acid, for example, hydrochloric acid, the reaction that occurs between hydronium and hydroxide, the reaction which happens there is actually between the hydronium ion and the hydroxide ion. So they react, and they'll form your final product. So this Na and Cl. So actually, what will react? These things will react. This and this. they will react.